Hey there, good to see you again. I'm Erwin Mazwardi. Today we are diving into the world of object-oriented principles. And don't worry, this isn't just theory. I'm sharing this with you so you won't feel lost when we start talking about more advanced stuff like UVM. Now, you might be wondering, why bother with object-oriented concepts in the first place? Well, over the years, I have noticed that many design and verification engineers, yes, even the experienced one, struggle with OOP. In my opinion, there are a couple of reasons for that. First of all, procedural code is just easier to follow. You see procedures calling another procedures right there in the source code, nice and linear. But with object-oriented, not so much. In object-oriented, what actually happens during runtime, objects sending messages to each other, that's not something that you can easily see. What you see actually is a bunch of class hierarchies, and that can be a little abstract. The classic way to explain the procedural code, you've got data and you've got algorithms working on that data. Makes sense, right? However, in OOP, you've got objects and they're supposed to be exchanging messages. Does that mean programs equals to objects plus messages? Well, not exactly. The real heart of object-oriented is this. Programming is modeling. That's it. That's the big idea. If you want to be successful with OOP, you've got to think in terms of modeling behavior. We do that by creating objects and wiring up how they interact. Here's where it gets really cool for us verification folks. A test bench and an object-oriented program, not that different. If you think about it, a test bench is just a network of components talking to each other. And OOP, it's all about interacting objects. It's a perfect match. Before jumping into UVM, we'll first use SystemVerilog to model our test bench components. SystemVerilog already gives all the object-oriented constructs we need. So then, if SystemVerilog gives us object-oriented features, why do we need UVM? Let me ask you this. Is it easier to build a test bench from scratch or to reuse one that already works? Exactly. Most of the time, reusing is the way to go. Building a test bench from the ground up is expensive and time-consuming. SystemVerilog gives you tools but not a structure. It doesn't teach you or it doesn't guide you how to build something reusable, layered, or coverage-driven. And even if you want to reuse something, good luck finding a reliable, proven test bench in your team stash. It's a hit or miss. That's where UVM come in. They are standardized, battle-tested methodologies, and guess what? They are built right on top of SystemVerilog using classes and everything we just talked about. So, before we get into the nitty-gritty of UVM, we are going to take a closer look at the object-oriented basic, stuff like classes, objects, and how they relate to each other. But all with examples pulled straight from test bench environments, and so it'll make sense. Alright, before we jump into objects, let's talk about something really important first, classes. You can think of a class like a blueprint or a prototype. It defines the stuff like variables and methods that are common to all objects of a certain kind. And here is the tricky part. Classes are kind of abstract. They don't actually do anything on their own. They just exist in your code and, well, in your head. We're gonna create a simple class. Let's call it a package. At a minimum, this package should have 4 pieces of information: source address, destination address, data, and CRC. These are the variables that describe the characteristic of any packet object we create from this class. Now, because we are doing object-oriented programming the right way, we don't just leave those variables lying around for anyone to mess with. We wrap them up and encapsulate them so no one can access them directly. That's where methods come in. They are like official ways other objects can talk to our packet. For example, we might have a method that computes the CRC and another one that display the packet contents and so on. Nice and clean. And just like that, we build a packet class. It holds data and operation that work on that data. Classes are awesome because they let us keep our code organized. They group data with the logic that belongs with it, which makes things easier to manage, especially in big projects or team settings. So that's the big idea. Classes are blueprints or templates. They don't do anything on their own, but they are the foundation for everything we build in object-oriented programming. They define variables and methods common to all objects of a certain kind. Next up, we'll talk about how to turn that class into something real, an object. Now that we have covered classes, it's time to bring those blueprints to life. Let's talk about objects. Now that we have covered classes, it's time to bring those blueprints to life. Let's talk about objects. A class by itself doesn't do anything, it's just a template. The real action, that comes from objects. Which are runtime instances of a class. So you can think a class as a cube plan and the object as the actual cube you built from that plan. Now let's walk through how to create one in SystemVerilog. Assume that we have memory location with hexadecimal address 0x1000, 0x1001 and 0x1006. To use those memory location, we need to use a pointer. Here we declare a variable called PTP, which has the type of packet, which will point to a packet object. But remember, right now it's just a pointer. The object itself doesn't exist yet. To create an actual object, you call the new function like this. What does new do? It allocates a memory location. It builds the object based on the class template. It gives your pointer the address to that object. And that's it. You now have a real object ready to do work. It's alive in memory and behaves just like we defined in the class. So remember, a class is the idea. An object is the reality. Next up, let's see what this object can actually do. In object-oriented programming, achieving a specific goal or system behavior requires collaboration between objects. Here we have object A and object B. Alone they don't do much, just sitting there quietly. But once object A can access object B through its interface and vice versa, they start working together. This interaction alone is already a form of behavior. For example, when the run method of object A is called, it in turn calls the run method of object B. This is exactly the kind of interaction we want in a test bench, objects collaborating to simulate behavior. Through collaboration, we create dynamic system behavior from simple individual components. Alright, so in order for objects to collaborate, there needs to be some kind of relationship between them, right? To really get what that means, let's walk through a simple example. Here, we are going to build a basic test bench set up with three objects: an agent, a sequencer, and a driver. And here's the behavior we want to achieve. The sequencer should be able to send package sequences to the driver. Both the sequence and the driver should be inside the agent. So what kind of relationships are we talking about here? Well, even though there are several types of object relationships out there, we are focusing on just two today: has A and is A. Let's start with has A, also known as aggregation. This simply means one object contains another. For has A relationship, in our case, the agent has a relationship with the sequencer and the driver. We want them all working together. The agent wraps them up and the sequencer sends package to the driver. To visualize this relationship, we use something called a UML diagram. That's a unified modeling language. Think of it like a blueprint for your code. UML helps developers see the structure and behavior of their objects before writing any actual code. For a has A relationship, UML shows a line with a filled diamond at the end connecting the container class to the content class. So if we translated that into SystemVerilog code, we got something like this. Here the agent class contains references to both sequencer and driver. The new function creates instances of those objects and stores them in pointers as QCR and DRV. Here are the corresponding memory locations of those objects. Now let's talk about the second relationship is A. This one's about inheritance. Means one object is a specialized version of another. For example, when we write this code, we are saying that agent is a kind of UVM agent. It inherits everything from UVM agent variables, functions, and adds its own special behavior. UML shows this with a line and an open arrowhead pointing to the base class. Usually the base class is drawn above the subclass with arrows pointing upward. This is super useful when you want to reuse functionality while adding more specialized behavior in your own class. So, just to recap, has A means one object contains another. Agent has a sequencer, while is A means inheritance, like agent is a UVM agent. Understanding these two relationships is the key to designing collaborative object-oriented systems like testbenches in SystemVerilog. And that wraps up our quick introduction to object-oriented programming for system-on-chip verification engineers. Hopefully, this gave you a solid foundation to tackle the more advanced and complex topics in UVM for chip verification. Thanks for watching. If you found this helpful, don't forget to like, subscribe, and hit that notification bell so you won't miss the next video. See you in the next topic.